Hello everyone, and welcome to my ELE419 project. My name is Batıray Aydemir, and I will talk about ALU design using electric VLSI. My ALU contains four main blocks: a subcomparator, multiplier, logical, and inverter blocks. I will talk each about them individually, starting with the multiplier. Now, in the left side here, as we can see, there are multiple versions of the blocks. Each version improved the last one, and the latest versions are used throughout the project. Let's start with the full adder. Now, in case of full adder, I did not use a traditional half adder then full adder design. No, I used the Euler path method to design this full adder. By this area required for the full adder is significantly decreased. And I used this full adder throughout the whole project. Like 2x2 multiplier, it used two of those. Or 4x4 multiplier, it used three 4x4 full adders and 20 AND blocks. I will talk about 8x8 multiplier, but as you can see, there are a lot of versions. I will talk about two of those specifically. Now, this is my main multiplier. There are four 4x4 multipliers, two 12x12 full adders, and one 8x8 full adder. And there is a selection part here. This selection part helps us to design a specific opcode for the multiplier to respond to. If it doesn't receive 0, 1, 0, the VDD wouldn't go through this selection block and wouldn't power up the system. Now, this design is my original and it is used throughout the whole project. And this helps us to lower the power consumption significantly. But in the case of the multiplier, there is one major problem. By adding this small selection block, the simulation time rocketed up to 3 to 4 hours. To receive just one output, I would need to wait 3 to 4 hours. So here I will show you my other multiplier version, which is placed in a digital bed frame. Here is the same multiplier without the selection blocks, and it is connected to pins of the frame. Now, let us simulate it here. Sorry, this is not it. Yes, this one. Let me run it. Now, my inputs are 1101, 1010 multiplied by 10101010. Now, let's see if it's correct or not. Here is the supposed output. I need to see this on my multiplier. And you can pause the video and check it yourself. It is exactly correct. Now, let us see another block of the ALU, like adder subtractor and comparator. Now, this is my own design as well. There are 6 selection pins. First 3 pins, the first 3 pins decide the adding or subtracting, and by subtracting I designed the comparison part here. Now the comparison part can use a little more cabling and block placement management, but it does the job nonetheless. Now let us simulate this too. Where is it? Here. Now let's run. Where is it? Yeah. Let me change this to 1 to 0. Now I want to see if these inputs are equal to each other. And spoiler alert, they are equal. Let me just give it the equality opcode, which is 01100. And when I give it, the equality pin has gone high. Now I will change B from 0 to 1, B6 pin, and now it will go low because they are not equal to each other. Here is the inputs, and let us see if A is less than or equal to B. Now less than or equal to opcode is 0, 1, 1, 1, 0, 0. And when I run it, here we can see the less than or equal to pin has gone high. It is working wonderfully. Now I will talk about one more block, the logical operator block. The cabling here, I love it. I really put my time into it. Now there are 5 selection pins. The pin tree, selection tree is used as don't care. And the power consumption I mentioned is really shows itself here, because these arrays of ANDs, ORs, XORs, XNORs are just powered up by specific opcodes. If they didn't receive their opcode, they would not work and they would not consume power. Now, let us simulate some of those. Oops, sorry. Now, there is my inputs 1100, 1111, 10101010. Let us end them. Now, the ending opcode is 10000. When we run it, here is our output. And you can compare it if you would like to. We would need to see 100, 1010. As you can see, it is the same. Let us XOR it. The XORing operation is this, and when we XOR it, we receive this output. And the correct output is this. As we can compare, they are the same. And lastly, the inverter. I will not show you the simulation because it just inverts the A to A not based on the selections. And this is my ALU. Like I said, because of the multipliers simulation problem, I cannot show you the simulation because it would take me several hours. And this is the whole project. Thank you for watching.